want to talk a little bit about the idea of pressure and volume, and we're actually going to clear up some kind of misconceptions that I think I may have caused. Now, I apologize for them, but I think this is a good chance for us to kind of reflect on the things that we've learned and also build up a couple of new ideas. So let's draw volume going that way and pressure going up. And one of the things I wanted to start with was the end systolic pressure volume relationship. You know, we drew something like this. We said that this is the relationship at the end of systole between the two, between pressure and volume. And one thing that I wanted to kind of bring up immediately was the idea of increasing volume. So as I go up this yellow line, I'm increasing volume. And sometimes the way I've drawn that, actually maybe I'll make a little bit of space on this canvas. Sometimes the way I draw an increase in volume can be a little bit misleading. So I've drawn, for example, in the past, I've drawn a left ventricle like this. And I've said, well, as blood goes into my left ventricle, it basically does this. You have more and more blood kind of filling up the heart. And I've drawn this sort of a picture. And it really does tell you about a couple things. It tells you that you have filling, right? You have filling happening. And that part I'm okay with. But the part that I'm not okay with is the idea that it basically seems like you have a fixed volume. It looks like you have a fixed volume on the heart, or the left ventricle anyway, and it almost makes it look like you're filling up a glass of water. Basically, that's kind of what it looks like a glass. And really, the correct way to think about left ventricular filling is a little bit more like this. You should be thinking of it more along the lines of a picture like this, where you basically have a smaller volumed left ventricle filling up with blood, and over time it kind of fills in completely. So it starts out like that, and then you add more blood and it becomes like that, and then you finally fill it up like that. So that would be the more accurate way of kind of showing what's going on in the left ventricle. And of course, all three of these then are the left ventricle at different points in time. So this second picture also tells you about filling. So you get the idea that blood is filling in the heart. But it does a better job of showing you that the volume changes. The volume of the left ventricle changes. So it's not fixed. And that's correct. This is the better way of looking at it. And kind of an analogy might be a balloon. You might think of a balloon for this filling process. So I want to be very clear that the left ventricle is not like a glass. It's like a balloon, in that it's not a fixed volume, it actually changes. So this is probably the more accurate way of thinking about it, and I apologize for doing this sort of a drawing. Truthfully, I didn't mean to confuse anyone, but I just wanted to kind of demonstrate filling, and I probably just did it in a quick and hurried way, and so I want to clarify that point now. So this is what it would look like, and actually I could take this a step further and say, well, what if I was to do this? What if I was to take kind of a cross section like that, cut it with a blade, you know, at these 3 points in time? Wouldn't you agree that you would actually get a kind of an interesting cross-section view of it? You know, if I was to take it like that and I was to erase these top bits out, and you were to now look down at the heart, you'd basically see kind of an interesting view, and I'll actually try to draw that view out for you. And it's helpful actually to do it that way, and I'll tell you why. So this one would basically look like this, and this one would look like this, and this one might look much larger than the other two, something like this. And again, this is just looking at a cross section, so it's nothing different at all, just looking kind of at the cut surface of it, and all three you'd expect to be full, right? So this is how I'm going to use our diagram. I'm actually going to use these kinds of images now to show what filling of the left ventricle looks like. So we can actually get a real kind of sense for it. And you'll see an interesting problem that comes up. So let's do that. Let's draw a couple of circles here. I'm going to draw, let's say, a big circle here where it's really large, and then let's say the volume is a little smaller at this point. So let's draw something like that. And the volume is really, really tiny. Let's draw something like that over here. Now, if you have these three volumes, you might say, well, okay, you know, you've colored them in. Well, one thing you'd have to admit, and you'd realize pretty soon, is that at the bottom of this curve, you have a small volume, but it does take a little bit of blood to fill that volume in. So when you have zero volume, like right here, there's zero blood in there, it would be an empty left ventricle. And then you'd actually add a little bit of blood to it. Let's say you fill it up, let's say halfway, and now you've got a half full ventricle. And then you keep doing it and you have a full ventricle. So you basically are kind of going this way along the curve. But until you have a full ventricle, and this is the point, until you have a full ventricle, you actually don't have any increase in pressure. So previously, when I drew out the end systolic pressure volume relationship with that yellow line, I drew it the way you see it now. But now I'm telling you that the truth is that it actually looks a little bit different, especially at the bottom end of this curve. So I'm going to erase this and draw it in properly. And this is the more accurate way of drawing it in. You'd basically have almost no, or really no increase in pressure. I shouldn't say almost no increase in pressure. And then once you get to a full ventricle, now you start seeing an increase in pressure. And really, the way that an increase in pressure looks is that you have a larger volume. And that's what you're starting to see, right? You start to see that larger volume. So even a tiny bit of pressure is going to push out on the left ventricle, and you'd actually notice that because now it gets larger. So the left ventricle actually doesn't change in size initially, and finally when the pressure starts actually mounting up, it starts changing in size. So you can start appreciating why I am saying that this first yellow line is incorrect. Let me erase it completely so it doesn't distract you. So I've drawn out the end systolic pressure-volume relationship, but what I want to do is now add to it our end diastolic pressure-volume relationship. And you know it goes something like that. And let me just label it in a yellow color just to be parallel. So this is our end diastolic pressure-volume relationship, right? Now, if I was to say, well, what would the cross-section look like? Now, let's just kind of choose a couple points. Let's say this is this point and this is this point, like that. And if I said, what would the same volume look like on the other curve, I would have to actually just kind of draw a line down and say, okay, this is this volume right here, and this is this volume down here. And along those points, let me actually just mark it on my other curve. Those points would be right there. And I actually could just similarly draw them out. I could say, well, this is about that. And then the other one looks maybe a little bit larger. It would be something like that. So these are my two curves, right? And I'm trying to make them look as similar as possible to the other ones, and I'll fill them in. So that's what the volumes would look like at these points. So really, when you look at the volumes, they look about the same, right? They don't look any different at all. And so you're left wondering, well, how in the world is it? And this is actually very, very confusing to think about for folks. How in the world is it that the pressure is so darn high on the end systolic curve, whereas it's low on the end diastolic curve, when they look the same? They don't look any different. And to figure this out, I think one easy kind of trick I've been using is to just imagine what's happening at the muscle level. So the muscle cells are kind of contracting and pulling in those Z discs, right? They're at the end of systole, you've got tons of contraction happening, and it's happening here too. It's in fact, it's happening at every part of this curve. And if I was to try to simplify this, instead of drawing hundreds of arrows like this, I could do this for every single point. Instead of drawing hundreds of arrows, you could imagine that I can actually connect all these arrows like this, and then I would have a similar effect if I just kind of drew it like this. I could simply draw almost like a rope or a band. Imagine a band or a rope that's pulling and tugging this way and this way. If I was actually to draw a band like that, you could imagine then it would be the same effect as the hundreds of little muscles that are contracting. And to take it a step further, you could actually even imagine people yanking on that band. So this is how I kind of picture it, just people yanking on that band. These are like two little workers, let's say, yanking on the band and pulling it in opposite directions. And if they were pulling in opposite directions, you'd basically have what we think of as contraction. You could have little workers that are basically yanking on all these things, yanking away. And by yanking away, what you basically end up with is a force of contraction. So this is basically how I imagine contraction, having workers yanking in two different directions. And if you had them going all around the heart in every direction you could possibly imagine, that is what a contracted ventricle is like. And because they're yanking so darn hard, because they're pulling so hard on this thing, you basically have a lot of increase in pressure building up on the inside of these ventricles. And you really don't have that happening on the other side, because on the end diastolic curve, I guess the question is, do we have any workers? Are they yanking? And the answer is no. The muscle cells are completely relaxed, right? They're relaxed. They're just kind of hanging out and taking a nap. You can imagine, your workers are really not yanking at all. And as a result, you don't have any of that increase in pressure. You have kind of just a very, very low pressure. And so that's the reason you can imagine there's a difference, even though the volumes are the same, that there's a difference in pressure. So a final kind of question that plagues a lot of people, and I'm actually going to make a little bit of space to answer it, is, so why is there blood in the ventricle at the end of systole? I mean, isn't that the point where all of the blood has exited the ventricle and gone into the aorta? Why is there any blood in there anyway? Shouldn't it be empty? And to answer this, to think about this, we can actually draw a pressure volume loop. I'm just going to draw it in purple just to create a little difference in color. And let's say that I have contraction right here, where I have a big purple dot. That's where I begin my contraction. So I'm going to draw going up from there like that. And let's say now my ejection is happening. And let's say it just rides over my picture of the worker like that. Let me actually draw one final volume piece, and that would be kind of, what is the volume here? Because we know that the volume is not changing there, it's constant volume, and at this point you begin ejection. So this is all ejection, right? I'm going to write ejection on the curvy part of the curve. So this is ejection happening right here over the hump like that. So ejection is happening between my two white lines, and here in the vertical part, I could draw a picture like this. I could say, well, my heart will be really full. So it'll look, in fact, let me make it bigger. My heart's going to be really, really full. Let me try to illustrate that nicely. So I could have something like this. I could have something like that. And if my ventricle is that big, if it's that large, let me actually just color it in now, then what's actually happening when I have ejection? Well, I'm going to cut and paste this little guy and show you on the top what it would look like. So let me just drag this little fella over here. And now this, if this is how I start out, then when I eject blood, you're basically going to have something like this. You're going to have an amount that goes away and an amount that's left behind. So the amount that's left behind is, of course, the amount that I showed you on the side. And I'm cutting it out, and this donut hole shape that's left, this is actually our stroke volume. This is our stroke volume. So you actually do have a lot of blood that goes into the aorta. Of course, that's important, and you have a little chunk that's left. So now you can see that you, at the beginning of contraction, you end up with having a lot of blood here. This is where you start, and then you lose a lot of blood. This is our stroke volume that you lose. And then you are left with a little bit of blood here. And that's at the end of systole. So at the end of systole, you do have some blood left, but you don't have nearly as much as you had when you began systole.